All right. Well, today is always a fun lab because today we actually get to make the Board of Education bots, the BOE Bots. Okay? So you guys are going to get to assemble your robots today and actually show them how to, and program them to navigate on the ground. Okay? So this is a very exciting lab. It's always a good time. You guys get to play around. We're going to make the lecture kind of short so that you guys have a good amount of time to get in there, put everything together, and play with the robots and make them work for you. Today is going to be the last day that we're working with the Board of Education. So when you're done, I'll ask you to please disassemble everything and put all the parts back in the bags where they came from so that the kits will be ready for the students next semester. So it's been a lot of fun working with the Board of Education, but we're going to be moving on after today. Okay? So we're going to start our lecture with a brief review of some of the concepts that we talked about last time. So we'll talk about motors and programming, because those are two things that are going to be very important today. So we'll briefly review how motors work, and then we'll talk about programming, especially the pulse out command and the for next loop, because those two things are going to be essential for getting your robot to navigate on the ground. Okay? And then we'll go on and talk a little bit about the BOE Bots. We'll discuss the goal for the lab and how you guys are going to work to complete that. Okay? Any questions before we get started? All right, cool. So let's talk briefly about motors. We discussed motors last time, and we said that most electrical motors involve two different kinds of magnets. Anybody remember one type of magnet? An electromagnet, exactly. And then what was the other type of motor? A permanent magnet. Yeah, right. The other type of magnet. Thank you. Permanent magnet. And these two types of magnets worked together in order to make a motor turn, right? We said that the simplest type of motor had permanent magnets on the outside, the north and the south pole. And then in the middle, there was the shaft, and attached to the shaft was a bar of metal. And we wrapped a wire around that bar of metal. And what did that bar of metal become when it had a wire wrapped around it and we passed current through it? An electromagnet, exactly. So by passing current through this wire, we created an electromagnet. And we could create that magnet so that the poles were like this. We had a south pole up there and a north pole down there. And we said that with magnets, opposite poles attract and same poles repel each other. So this south pole would be repelled by this other south pole. The north pole would repel the other north pole, and that would cause the magnet, and therefore the shaft, to rotate around like this, right? So the shaft is sticking out of the board like this, and the whole magnet is rotating around in this direction. So it goes on for a while, and eventually the south pole comes down and gets almost right next to this north pole, and it seems like it would get stuck. So what do we do in order to prevent the south pole from getting stuck there?
Switch wires.
Yeah, we reverse the polarity on the electromagnet by reversing the direction of the current. When we push the current through in one direction, we have a south pole up here and a north pole down there. When we switch it around, the position of the poles switches as well. So that's what we do in order to keep the magnet rotating and keep the motor spinning. So any questions about that? Yeah?
Does it matter direction which it turns? Clockwise, counterclockwise? Or pretty much works the same way?
So it works the same way. If you...
Or how do you make it to turn like clockwise or counterclockwise?
Yeah, so right now, what's happening is that we have the electricity flowing through this magnet in such a way that the force is turning it in the clockwise direction. If we wanted it to spin in the other way, what we would do is we would just reverse the flow of electricity right now, so that we had a north pole up here and a south pole down there. And then that north pole would be attracted to this south pole would be attracted to that north pole, and so it would spin in the opposite direction. So you just, depending on which way you apply the current and at which point your motor currently is situated, that's what determines which way the motor is going to spin. This is kind of the simplest configuration for a motor. So it's not really easy to tell exactly where this shaft is, but there are other things that you can do so that you know exactly where the shaft is. There are things called encoders, which are connected to the shaft, which are basically little wheels that tell a computer exactly where this electromagnet is, what position it's in. And if you had an encoder on there, then you could know exactly where the shaft was, and based on that information you could apply the electricity in the way that you want, so that the motor turned in the direction that you want. Yeah. Other questions? Yeah.
So, like, with the moving part, how are you gonna get like the power,
the electricity
it's
to there?
moving, so
Right, exactly. So I've drawn sort of a simplified version because in my drawing the wires just sort of hang out in space, and of course if you had real wires hanging out inside of a motor, they would get all tangled up when the motor turned around. So what's actually happening is that if you were to look at a close-up view of the shaft, it would look something like this. You've got the motor shaft here, and then one side of the shaft would have a metallic coating on it, something like this. The green represents a metal coating, and then one of these wires would be attached to that metal coating, and then there would be a metallic or a carbon brush that contacts that coating, so that the brush stays stationary and the shaft rotates around like this and makes contact with that brush, and then the brush transfers the electricity from the outside world to the shaft. Does that make sense? Yeah, and that's why they call this type of motor a brushed motor, because it's these brushes that transfer the electricity. Yeah?
So brushless motors, they have static magnet in the inside rotor.
Permanent magnets. Yeah.
Permanent magnet.
Yes, that's exactly
right. So it doesn't
right.
need any power for this.
Exactly. So a brushless motor would be more like this. You have the permanent magnet in the middle, like you said. So, for instance, you'd always have a north and a south pole like that, and then you have electromagnets around the outside, like this. And just like you said, we don't have to transfer any electricity to the middle rotating part anymore. So there are no brushes that we need. So if we call this a brushless motor. Okay? So this is a brushed motor. Brushed DC motor. This one is a brushless DC motor. Okay? So the thing about the brushless motor is that you need to have an encoder on the shaft in order for it to work, because you need to know exactly where it is so that you know when to apply the power to these outside magnets and when to switch the polarities of these outside magnets. So you need to read the position, and you need to have a little computer that is doing that all the time and applying the power as necessary to these magnets. With the brushless motor, all the transfer is physical. So there's actually another coating on this other side of the shaft. And what happens is that when the shaft is in this position, like it currently is in, the electricity is going through the winding in one way. But then when it rotates around and the brush makes contact with this purple side, that's how it reverses direction and pushes the electricity through in the opposite direction. So with a brushed motor, you don't need to have any sort of computer that is monitoring it. It's purely a physical connection that switches the direction of the current. With the brushless motor, you need to constantly have a computer monitoring. So what do you think might be some of the advantages of a brushless motor? Or I'm sorry, of a brushed DC motor?
Simple.
It is simpler, exactly. Yeah, you don't need the computer, so it's simpler. You don't need the encoder. And why is it good when something is simple?
Easier to fix.
Easier to fix, yeah.
Just replace the brush.
Cheaper, exactly. Yeah, all of those things. So it's simpler, cheaper, all of those things. What might be a disadvantage of a brushed motor?
Cheaper.
The brushes can wear out.
Yeah, the brushes can wear out, exactly. This is a physical contact, and you have a physical item rubbing on something else, so it will wear out over time. Yeah. Also, this is not a perfect connection, so there's some resistance, so it's somewhat inefficient. And finally, you can actually get some sparking between the brushes and the shaft, which is also inefficient and can be dangerous in some cases. So they're cheaper and simpler, but they are less efficient, and they can be prone to sparking, and you can have parts that wear out over time. Yes?
So for the brushless DC motor, when you say a computer,
Yeah.
is it like the controller on the drone?
Yeah, it's a very, very small computer. I mean, it's not like a desktop or anything like that. It's,
Yeah.
like minuscule, but it's still a processor nonetheless.
It's kind of like a sensor to terminate, or some sort of, on the shaft. It gives signal to the computer, and
Yeah.
the computer decides.
Exactly, exactly right. You've got some kind of sensor to figure out the shaft position, and then the computer reads that signal and determines when to turn on and turn off these.
It's pretty much very basic computer, right?
Huh?
Basic computer.
Yeah, very, very simple computer. Yeah. Mhm. Yeah, so that's a quick review and a little more information about motors. Any questions about that? Yeah.
I have a question about the motor we use like on the lab.
Mm-hmm.
It's a servo motor, right?
Yes.
So I don't know, like before I watched a couple of videos, like when they say the servo motor can turn like 360, then it will stop, you can't turn it anymore. Then you have to turn it back. So how the bots will keep going?
Right. There are two main types of servo motors. One is called a positional servo motor, which is kind of what you're talking about. What happens with that type of motor is you send it a command and you tell it what position you want to go to. So you tell it a certain number of degrees, and then it'll go to that position. So you can tell it 90 degrees and it goes here, 180 degrees and it goes over there, and then 0 degrees it goes back to the start. So you can tell it which position to go to, but it has a limited range of motion. It only goes, typically they don't go more than about 180 degrees, maybe a little bit more. So you tell it which position to go to, but then it can't go beyond a certain range. The other type of servo motor is the one that we're using, which is called a continuous rotation servo. With that kind, you don't specify a position, you specify a speed, which is what we saw. And you tell it how fast you want it to go, and then it goes that speed. And that type of servo, the continuous rotation servo, can rotate forever and ever. There's no limits on that type. Yeah. So let's talk a little bit more about servo motors. We said that servo motors were kind of like DC motors with an extra brain attached to them. So this little computer brain inside of a servo motor listens for commands and then controls the motor in order to do what the commands tell it to do. So that's what we were doing last time. We were sending commands to our servo motor to tell the servo how fast to turn, and then the little processor inside the servo was receiving those commands and controlling the motor to make it turn at the speed we wanted. So we said that all communication has to happen with a certain type of protocol. All electrical communication uses some kind of protocol. The protocol that we used was a series of voltage pulses like this. And these voltage pulses told the servo motor how fast we wanted it to turn. So what exactly was it about these pulses that specified the speed that we wanted?
Milliseconds?
Yeah, the millisecond duration, right? So we could say the duration controls the speed. So anybody remember what duration caused the motor to be stopped? Yeah. So 1.5 milliseconds
750.
told the motor to stop. What was the longest duration we could have?
2 milliseconds.
Yeah. So 2 milliseconds equals full speed. Then I'm going to say that's clockwise. I never remember which one is which, but just for example, that'll be full speed clockwise. So then what was the shortest duration we could have?
1 millisecond.
And what did that tell the motor to do?
Full speed counterclockwise.
Yeah, full speed counterclockwise. So by changing the width of the pulse, we were able to tell the motor how fast to go and in which direction. So the closer the duration was to 1.5 milliseconds, the slower the motor would turn. The closer it was, or the farther away from 1.5 milliseconds, the faster it would turn. Now, we used a particular command in order to create these pulses. That command was pulse out. And we said it'd be really nice if we could just say pulse out and then specify a certain number of milliseconds, but it wasn't quite that easy. We had to do translation. So we would do something like pulse out and then the pin number. We were using 12. And then what number would I use if I wanted to make the motor stop? 750. Yeah, so this was the number of clock cycles. So there was this weird translation between clock cycles and milliseconds, but 750 clock cycles was stopped. And then if I wanted it to go clockwise, what number would I use for full speed clockwise? I'm thinking about this one. So, yeah, 1,000 equals full speed clockwise.
But I have a question.
Yeah.
Since we're working with a left and right motor,
Yeah.
on the machine, wouldn't it be opposite, all right? Because you want the other one to go counterclockwise.
That's exactly right, and that's a really subtle point. Not many people recognize that at first, but you're exactly right. What's going to be happening today is that we're going to have two motors on our robot, and we're going to want our robot to drive forward. But what's happening with our robot is that we've got these two motors, and one is on my right, your left, and the other one is on my left and your right. So if we want both of these motors to drive the car in the forward direction, we will actually have to tell one of them to spin clockwise and the other one to spin counterclockwise, because they're on opposite sides of the car and they are flipped over. So yes, so that's a very good point. We're going to have to do that. Thank you for mentioning that. So we will have to tell one of the motors to spin clockwise and then the other one to spin counterclockwise. And the number, the fastest speed you can go counterclockwise, how many?
Counterclockwise?
Yeah, counterclockwise, that was
500.
500, exactly. So those are the commands that we can send to the motors in order to control their speed. And now we also used another set of commands to control the duration, the amount of time that the motor was turning in a particular direction. You remember what we used to control the amount of time the motor ran?
The cycles between commands is 20 milliseconds.
Yeah, so exactly. So hang on one second. So like you mentioned, there's 20 milliseconds between each of these pulses, but that part never changes, right? So what could we change in order to affect the length of time the motor runs? Yeah, the number of pulses, exactly. So if we just send one single pulse, the motor will start turning at that speed, but then it'll stop almost immediately. We have to keep sending these pulses as long as we want the motor to keep turning. So like you said, the more pulses we send, the longer the motor turns. And what did we use in our program to send lots of different pulses? Or lots of pulses over and over again, I should say. A for next loop, exactly. So we said something like for counter equals 1 to 100, and then we put the code in the middle to actually send the pulses. And then at the end, we put this next to tell the program that our loop was over. So we would start here, we would go send a pulse, we'd get down to next, we'd come up and we'd repeat, and we'd do that over and over again as many times as we specified. So if I put a higher number here, we're going to send out more pulses. So that's going to make the motor run for a longer time. If I put out a lower number here, that's going to create fewer pulses and the motor will run for a shorter time. So when we use the pulse out command, we can control the speed of the motor. And when we use the for next loop, we can control the duration that the motor is running, the amount of time that the motor runs. So together, when we put speed and duration together, what we're really doing is controlling the distance that the motor turns. You guys saw that when we controlled the windshield wipers last time, right? We could have the windshield wipers going really fast, and when we did that, we had to make them go for only a short period of time, right? In order to go 180 degrees. Or we could have them running very, very slowly, and when we had them run slowly, we had to make the duration much longer. So together, the speed and the duration determine the distance that the motor runs. And we're going to find that that's necessary today because we're going to need these robots to roll forward a specific distance and then stop and then roll forward again. And what you're going to find is that we'll give you a program to start from, but it'll have the basic outline, but the distances are not exactly right. So you guys are going to have to adjust the distances. So you can use the speed and the duration that the motors run in order to adjust those distances. Okay? So any questions about that? All right, cool. So then let's go on and talk a little bit about the BOBots and the goals for today's lab. So you guys may have noticed that we have little patterns laid out on the floor in room 320. The patterns look something like this. There's a starting line, and then one leg here, and then a bar across, and another leg, and then a jog over here, and then we come over here, and then there's a parking spot at the end. So what we want you guys to do is program your robots so that they follow this course. Okay? What they're going to do is they're going to start off here at the bottom, then they're going to roll forward, and they're going to stop at this first cross piece. And then they're going to wait there for about 3 seconds, and they're going to beep. Okay? You guys are going to hook up a little speaker, and they're going to beep when they get there. Then they're going to get rolling again. They're going to come here, and they're going to turn. Then they're going to go down here, turn, go over here, and then for the final leg of their journey, they're going to turn around and they're going to back up. They're going to back up, and then they're going to park themselves completely inside this parking spot at the end. Okay? So that's your goal for today's lab. That's what we're going to be aiming to do. Now, like I said, we're not going to throw you in at the deep end and make you start from scratch. We're going to give you a program to start from, but it's not going to be perfect. You guys are going to have to fix some bugs and make some modifications in order for it to work the way you want. Okay, so for instance, we're going to give you a program that makes the car run for this first lap, or for this first leg and then stop, but it's not going to be exactly right. So your car is not going to stop exactly on the line. It's going to start here and it's going to go, and it might end up somewhere up here. So you're going to have to fix that so that the car stops right on this line. Okay? Then it's going to wait, and it's going to come, it'll drive forward, and then it'll turn, but it might not turn exactly the right amount. It might turn too much. So it might end up turning over here and then driving off this way. So you'll have to fix the turn so that it turns and goes in the correct direction. Then it'll come over here, and it might not have this turn at all. So you're going to have to add this turn in. And then I think it's missing this leg also, so you're going to have to add this leg in. And then finally it'll back up, and you'll have to adjust the distance so that it backs up and lands right in that spot. Okay? So it's going to be a good starting place, but it's not going to have everything that you need. You're going to need to make some adjustments. All right? So let's take a look at the code that we give you and see what you have to work with. before we get to that, I should say that there is a little bit of testing you can do with your robot after you've assembled it. So the first thing you're going to do when you get into the lab is you're going to put this robot together. There's instructions in the lab book for how to do that. Once you have it together, you might want to do a little bit of testing. Okay? So in order to test it out, you can go to the L02 Stamps 2 folder, and then there's this one called BOBot Assembly and Testing. Inside here, there are several programs that you can use to test out your BOBot. So, for instance, there's this one called Left Wheel Ahead, and when we run that, it should make the left wheel turn in the forward direction. Okay? So, similarly, there's a right wheel ahead and so on. So you can try those out. If you find that your two wheels are going backwards, all you have to do is take the one that was connected to pin 12 and move it into 13, and take the one that was in 13 and move it into 12. Okay? If you reverse those, then the directions of the motors will reverse as well, and your car should start going forward. Once you've got everything assembled and tested, we can move on to the actual program. So that's under L03 Warehouse, and the program you can start with is called Warehouse New. So again, this is a place where the comments are really going to help us out. So,
Can you make the record bigger?
yes, thank you. All right. So this is where comments are really going to help. For instance, we have this comment that is talking about the first leg routine. So this part of the code is referring to this first leg of your journey, which is right here at the beginning of the navigation, like we talked about. Okay? And then there's a part that says pause and beep. So you remember I said that when we get to that first crossbar, the robot has to stop and create a beep. So that's what's happening there. And then there's a second leg, a left turn, third leg, and so on, right turn. Now you'll notice that there's no fourth leg in there. There should be a fourth leg, but it's missing. So you guys are going to have to add that in. You're going to have to add in another turn. And then this program does include the reverse, which is where you back your car into the parking spot. Okay? And then there's a command that says stay still at the end. So just like you pointed out earlier, one motor has to turn in one direction and the other motor has to turn in the opposite direction when we are trying to make the car drive forward. Okay? Since the motors are on opposite sides of the car. This program already does that, but it's very important to be aware of that so that you understand what's going on. Otherwise, you might look at that and think that there was something wrong with that. Okay? So that's what's happening there. And then similarly, when you want the car to turn, you want one motor to turn forward and the other to turn back. So you actually have to send commands to the motor to make both motors turn in the same direction. So they would both be turning clockwise, for instance, but one of them would be on the left and one of them would be on the right. And so one of them would be turning forward and the other would be turning reverse. Okay? And that would cause the robot to spin in place. Okay? So that is what's happening there. So do you have any questions about how to do the program or what you're going to need to do there? Okay. I have a couple of assembly tips for you when you're putting your robot together. The first one is the most important, I think, and that has to do with where or how you attach the servo motors. Okay? So if you look at the servo motor, you can see that it's asymmetrical. What I mean is that the shaft of the servo motor is closer to this side of the motor than to this other side. Right? You can see that the shaft is right here. It's close to the left side on the screen. It's farther away from the right side of the motor. So you can orient this servo motor in one of two ways. You can either have it oriented with the shaft towards the middle of the car or towards the front of the car. You really need to have it oriented towards the middle of the car. That's the important thing. So you want the shaft to be close to the middle of the car. The reason for that is that it puts more of the weight on these wheels and less of the weight on the back caster. And that's important because these wheels are the ones that are doing the driving. And so you want to have as much weight and as much force on these wheels as possible. If you put it around the other way, there's less weight on these wheels and they tend to slip. The problem with that is that slipping is not very predictable. So it might slip more this time and a little bit less next time. So you run the car and it slips a lot and it doesn't go very far. So you turn up your distance. And then the next time you run the car and it only slips a little bit, and so your car goes much farther than you wanted. So then you turn down the distance, and you can see it's really frustrating. It's just not consistent. So you want to put the shaft towards the middle of the car so that you get as little slip as possible and your car is as consistent as possible. Okay? Really, it drives people nuts if you put it the other way. It seems like such a subtle difference. You might think it wouldn't have an effect, but it actually makes a huge difference in the performance. So you really need that shaft to be towards the middle of the car. Okay? Questions about that? All right. So that's the first tip. The second thing is that the instructions talk about a battery pack that gets screwed in and uses permanent batteries, or non-rechargeable batteries. We have these nice rechargeable battery packs, and we use them all the time. We have to put them in and take them out. So instead of screwing things in, you're just going to take the battery pack that already has Velcro on it, and you're going to Velcro it to this little patch. Okay? Also, you just want to leave this wire loose, hanging out, and wrap it around the edge of the car so that it can be plugged into this port pretty easily. The instructions tell you to route the battery cable through this hole in the middle, but that's kind of cramped and the end of the cable doesn't fit through there very well, so it's a hassle. So it's better and easier just to route the wire around the outside of the car. Okay? So that was all I wanted to say about the assembly. Do you guys have any questions about any of that? Yeah.
Just a question about electrical cars, like Tesla cars. Is that kind of the same principle they work, or like the two motors and axle, or a little different? The basic principle.
Well, I mean, the basic principle is the same. They've got little batteries, and they route the batteries to motors that power the wheels. I'm not sure whether it's independent motors or whether, I believe it's just a single motor, and then they steer the car in the way that other cars are steered by turning the front wheels. So I believe that's what's happening.
But pretty much the way the programming is kind of very similar to what we do in principle. I mean,
It's a little more complicated.
but like yeah, because different speeds and stuff. But still, it's really interesting.
Yeah, yeah. I heard an interesting fact, which is that the batteries that they use are actually about the same size as these AA batteries that we use. They just use thousands and thousands of them.
Yeah.
Yeah. So, so there's that. The type of motor that they use is actually a slightly different kind of motor called an AC electric motor. So what happens with an AC electric motor is that you have the electromagnets around the outside of the motor, and then in the middle you basically have a fancy coil of metal. And what happens is that you put alternating current through the coils on the outside of the motor, and that alternating current creates a magnetic field, which then creates a magnetic field in the coil that's in the middle, and that causes the middle shaft to rotate. So there's no permanent magnets in an AC motor. There's just the electromagnets around the outside and then this coil in the middle. And they do that because when you create the magnetic field that way, you can actually create a much stronger magnetic field than you could get out of a permanent magnet. So AC electric motors are the kinds that are used in large industrial applications like electric cars, like electric trains and things like that. So the same principles of electricity and magnetism apply. It's just, again, a slightly different configuration of where the magnets are and how they work. Yeah. Other questions? Okay, cool. Then I will take attendance and I'll let you go. Like I said, this was a slightly shorter lecture so that you guys have lots of time to work on these, but I think they're a lot of fun. Oh, also, when you get your car working and it's looking cool, feel free to take a video and show your friends. You know, this is always something that people like to see. It's always a lot of fun to show off that you've made a robot and got it to navigate by itself. So take a video. Yeah, there you go.